Welcome. The title of today's notes is Inverse of a Matrix. And this will give us the fourth method to solve a system of equations. I think I've said this before, of course, but we've had substitution, we've had elimination, we've had Cramer's rule using determinants, and now we're going to use matrices. In fact, we're going to sort of apply an inverse of a matrix in order to solve a system. So we'll take a look at this. We're going to do some stuff by hand, mostly on the 2x2s, and then when we get into the 3x3s and the 4x4s, we're going to let the graphing calculator do some work for us. So let's start it out here. At the very top it says inverse of a matrix. So if I have a matrix A, as you can see right here, its inverse will be denoted by this piece right here, A inverse. And we've actually seen that notation before talking about functions. And so there's a formula that's used for finding the inverse. And as you can see, just off to the side, it does say if the determinant is not 0. So you're going to see momentarily that this formula does require use of a determinant, so another context for using that. And let's go ahead and give it a try. So I have 4 values making up my rectangular array of numbers, and again we're going to be doing this on the squares, so 2x2s and 3x3s, etc., etc. And so in this case, for the 2x2, the inverse would look something like this. It's 1 over its determinant, and so you're going to have to find the determinant of those 4 values making up the matrix. And that becomes, that 1 over the determinant becomes a scale factor for a different matrix right over here. And so you're going to multiply that 1 over the determinant into another 2x2 matrix, and that 2x2 matrix is made up of the 4 elements of the original except modified. And so here's how it works. The A and the D, let me spot those 2 things in the original. So everyone take a look. The A and the D on the main diagonal switch positions. So this becomes D and this becomes A. The B and the C on the secondary diagonal, that's what I referred to when we talked determinants. So on the secondary diagonal, very simply switch signs. So this becomes the opposite of B and this becomes the opposite of C. So I don't know what you want to write off to the side here. I'm going to write this, and if you feel like it's worthwhile, then do the same. But main diagonal, switch terms. So A and D switch to D and A. And then the secondary diagonal, and again, excuse my shorthand here, I think it'll work there. The secondary diagonal, switch the signs. By the way, I do have a proof of this in my possession if you want to take a look at any time. I think I have it on an old overhead, and you're more than welcome to ask about it and take a look and see kind of where this comes from. It uses just some calculations from a linear algebra class in order to kind of work with it. But basically the premise would be, as we saw in the previous notes worksheet, if I was to take the original matrix and multiply it by its inverse, which again happens to be this complex thing right here, I would get the identity. Any 2 matrices that are inverses of one another multiply to that 1, 0, 0, 1 in the 2x2, the identity matrix. So again, if you're interested, I do have a proof for it. If not, no big deal. We'll just utilize it, of course. So there's no time like the present here to get a little practice with it. Just a basic one to start, and then we'll see its connection to systems momentarily. So here's how it's going to play out, everyone. I have just a nice 2x2. -2, 2, 5, and -4. And so what I'm looking to find, of course, is the inverse of that matrix. Now again, not every matrix has an inverse. This one I do know does, so let's go ahead and figure it out. So the way we pull this off is very simply find the scale factor first, and the scale factor is 1 over its determinant. So -2, 2, 5, and -4. And when I have that, I'm going to multiply that scale factor into this modified matrix over here. And that modified matrix basically does 2 things. The main diagonal switches the positions. So the -4 moved up, the -2 moved down. And the secondary diagonal switched the signs. So that would be a -2, and this would be a -5. Now obviously you can see we have just 2 things to take care of here. Number 1 is to find the determinant, that is the denominator of this scale factor right here. I'm going to circle that on my screen. And then once we have that, then this is going to distribute essentially into each of these four values, as I'm trying to show you there. So let's see what we end up getting. So first and foremost, let's see what this piece is. Again, don't forget determinant, that calculation. So main diagonal product minus secondary diagonal product. So -2 times -4 minus 2 times 5. And I end up getting 8 minus 10 when all is said and done. So it's -2. And so you can see essentially the scale factor here is -1/2. I hope everybody is all right with that because that -2 is in the denominator. I'll tell you how I sort of think about it. And if you like that, use it. If not, no big deal. So again, this officially, the way this is supposed to work out, this then becomes the scale factor of this matrix, so of these four elements right here. The way I like to think about it, instead of multiplying by the 1 over -2, I basically take each of these four elements and divide by the determinant. So one more time, I'll take the -4, divide by this, -2, divide by this, -5, divide by this, and -2, divide by that. So that's how I think of it, because obviously it is a 1 over situation. So I just take my numbers from my modified matrix and divide by the determinant. And running out of a touch of room here, so I'm going to bring it over here. Sorry about that. But basically we would find when all is said and done that if I do -4 over -2 is 2. -2 over -2 is 1. -5 over -2 is 5/2 or 2.5. And -2 over -2 is 1. And that would be the inverse. Always a good way to check on the calculator there if we wanted to, or just if we had the time and inclination. Remember, any two matrices that are inverses of one another, if we multiply them together, we should get the identity. In this case, that would be 1, 0, 0, 1. Okay, so that's how it's going to play out here. We'll get, again, some practice on that piece as we go through this process. But you need to be able to find an inverse of a 2 by 2 in order to pull off the next piece. So let's start putting it back together here a little bit. It says on your paper, solving a system using matrices. And we're going to do a 2 by 2. And so here's the premise. I have a basic 2 by 2 system right here. And we could solve by elimination, substitution, Cramer's rule. But there's also a fourth method using the concept of matrices. And so what we're going to basically do is rewrite that entire system as a product of matrices on the left-hand side and as really a 2 by 1 matrix on the right-hand side. And so here's what's kind of fascinating, especially about the left-hand side of the system. These four numbers actually can be written as a product of two matrices. You wouldn't necessarily see it, but once I put this together, it should actually work out nicely. So watch what happens. I take the coefficients of the x's and y's, and I literally make a 2 by 2 out of it. So 2, -3, -5, and 8. And again, the 2x minus 3y and the -5x plus 8y really represents the product of that matrix and a secondary 2 by 1 matrix, which would look like this right here. And try to see that. What if I asked you to multiply those two matrices together? Think back to yesterday's lesson where you would go across the left matrix, so top row on the left matrix, and match them up with the column in the right. And you see I'd get a 2x plus a -3y. And then you would repeat for the bottom row. You would go across the bottom row and then match it up down that column right there, and you would get a -5x plus an 8y. And so what's kind of fascinating is these four values, well, the product in each case, those four, come from these two matrices being multiplied together. Okay, well, I said the right-hand side is just the 2 by 1 there, and so let's actually just write that 2 by 1. And so the goal, of course, is to solve for the variables, to find out what x and y would be equivalent to. So at this stage, here's, I guess, what I would ask. Put this as, we'll call that our matrix A. We're going to call this our variable matrix. So I'm going to put a big fat X there just as our variable matrix. And then this one on the other side would be matrix B. And so the question would be, of course, how would you solve for the variable matrix? How would you get this by itself? Now your standard answer, of course, would probably be, oh, let's just divide by A. Take matrix B and divide by A. And that's not quite the context that we're going to look at. What we're going to do as an alternative to that, instead of dividing by A, I still want to get rid of this. Well, how do I sort of get rid of it? I'm going to multiply it by its inverse. And so what I'm going to do, actually, you know what? Let me just, sorry, erase that piece. Let's come down one so you have a little room to write this stuff. But basically what I'm going to do is multiply it by its inverse. And think what happens when I multiply two matrices that are inverses of one another. I end up getting just that identity matrix. And that identity matrix obviously has no effect on this. So the identity times this variable matrix is the variable matrix. And then anything I do to the left-hand side, of course, everybody, I have to do to the right-hand side. Now remember, when you multiply matrices, order does matter. That is for sure. So in order to pull this off, actually, the inverse of A does have to go to the left. So what happens when all said and done here? Well, exactly what we're going to see. So the variable matrix, which is now by itself, because basically, you could kind of track it with my pen here, those are going to cancel out. And I end up getting my variables would be equal to the inverse of A times B. So watch what happens. Let's kind of see this in action with this one. We'll use the calculator for this one, and then we'll do a couple manually, and then we'll pick the calculator back up. So I guess the premise would be to find this piece right here. Okay, and I'm going to find the inverse of matrix A, and I'm going to multiply that by the 10 and 26 of matrix B. I hope everyone's okay with that piece. Now, again, I should be asking you to come up with the inverse of this right here. I'll do that on the next one. So why don't we do it for the first time just on the calculator using, well, the calculator is obviously set up to use that formula. So I'll tell you what, we know what matrix A is. Let's go into the matrix menu right there, and let's edit on A a 2 by 2. Okay, and so I would get 2, -3, -5, and 8, everybody. Okay, and what I'm going to ask the calculator to do is come up with the inverse of that. And so remember, all the calculations are performed on this main screen right here. Here's how it plays out, everyone. What I'm going to ask you to do is hit second, well for me, get into the matrix menu, and let's name A. And then I think we've potentially seen this button before. Let's see if you can kind of catch it as I'm circling it. Does everyone see that little -1 right there? It has different contexts for, well, different operations for different contexts, but in this case, it's going to be the inverse. And so that's how we represent A inverse on the calculator, and notice what it gives us. It gives us our 4 numbers there, 8, 3, 5, and 2. And so everyone, I'm going to go back to my screen and write 8, 3, 5, and 2. Now, let's see if we can do this without the calculator. Again, just trying to mix and match here technology. If you want, you're more than welcome to kind of beat me to it and actually now type in A, this is matrix A. Well, this would be our A inverse. So we could do this times this on the calculator. That would be fine. But basically, watch what happens when we do this. I'm going to do it manually. And so I would now multiply these two together. Remember, it's a 2 by 2 and times, in this case, a 2 by 1, which means it's going to be a 2 by 1. And so now look at the correspondence here. X will be this number, and Y will be this number. That's kind of the beauty of the way this sets up. One more time on that. 2 by 2 times 2 by 1 is 2 by 1. And I don't mind doing this piece right here. It's funny, I think I have something. I know what I did wrong. There we go. That was a negative. I hope you guys caught that. And that was a negative. There we go. Again, just make sure you keep track of everything, unlike your teacher there. But it looks like I caught it at the end. Alrighty, so the 10 and -26 go there. Now this looks good. So remember how we're going to play this off, everybody. I'm going to go across on the row and down in the column there. Left matrix across, right matrix down. And so 8 times 10 is 80. 3 times -26 is -78. And so I have an 80 and a -78. Combine those together, and you get 2. This one right here, everybody, watch. Repeat the process. Across the row, down the column. 5 times 10 is 50, everyone. 2 times -26 is -52. So I have a 50 and a -52. 50 and -52 make -2. And look at that. Equality, x is 2, y is negative 2. And if we want, just as an ordered pair, that's exactly what I'll write. 2 and negative 2. I won't waste your time, but if I plugged each of those numbers back in for x and y here, would it balance both those equations out? Sure, most definitely. So yeah, it looks a little cumbersome by hand here. I'll ask you to just do a few of those, but you'll see when we hit the graphing calculator, it'll be a nice way to pull this off. All right, so let's do 2 together all the way through. Now just remember, always, always, always when you're doing this stuff, it's inverse of A times B. So inverse of A times B. So here's what I'm going to ask you to do. Try to pause the video and find the inverse yourself. I will walk you through step by step, but I am going to do it rather quick with the thought that you have already accomplished it, and then you're just seeing if you got it right. So what I'm going to ask you to do is find the inverse. Then we'll perform the multiplication. So let's see if we can do this, pretty much manually and kind of go from there. So please pause the video and then come on back and we'll see if you got the inverse right. Okay, so let's see how you did. When I pulled this off, I first of all did 1 over the determinant. And so it's that piece right there. And that 1 over the determinant is our scale factor into this modified matrix over here. Again, change the places of these two. Main diagonal, switch spots. And then the secondary diagonal just switches the signs. And so that would be a -1, and this would be a -6. In this particular case, it does look like my determinant is 8 minus 6. So it looks like a nice 1 over 2, or a 1/2, is going to be multiplied into each of these 4 numbers right here. So again, 1/2 gets distributed in. The way I've always kind of thought about it is just take each of these 4 numbers and divide by that number down there, divide by the determinant. And so if I do that one at a time for all 4, -2 divided by 2 is -1. -1 divided by 2 is -1/2. -6 divided by 2 is -3. And last but not least, -4 divided by 2 is -2. And that, everybody, is the inverse. Step 1. That looks great. And now the way we're going to play this out, very simply, our x and y, and I'm going to have to kind of move it over just a little bit, but very simply, our x and y, our variables, are going to be the product of the inverse of A times B. And in this case, I'll get my numbers right there. There we go. And that's exactly what we would do. So I'm sorry, I'm going to have to kind of come up and do this last piece here. But again, I would ask you to pause the video, see if you're on the right track. Can you multiply these 2 in? And I'll just give you a heads up here again. When we multiply a 2 by 2 by a 2 by 1, it should be a 2 by 1. And so make your 2 by 1 up. Again, I'm going to come right over here and pull this off. So xy is equals, and again, it's a 2 by 1, and so you notice they match. X will be the top, y will be the bottom. So again, pause the video, please do your multiplication, and then come on back with it. All right, let's see how you did. So row on the left matrix, column on the right matrix, match them up. This matches up with that. So -1 times 5 is -5. -1/2 times -9 is 4.5. -5 and 4.5 added together would be -1/2. And in this last one right here, again, row on the left, column on the right, numbers match up. -3 times 5 is -15. -2 times -9 is 18. I get a -15 plus 18, and that's 3. And there, everybody, is the solution to your system. Plug them back in, perfect harmony. Okay, looks great. So now that is the 4th way to solve. And let's try one more. Just watch what happens here in this case. Again, I would kind of set it up as finding the inverse first. So let's go for it right away here. And I'm going to do my setup with you. You don't have to pause the video here. Watch what unfolds. I'm kind of looking at these numbers and seeing it right away. But I'll go through sort of the motions there. Switch the main diagonal. Switch the signs on the secondary. And let's go for it. So in this case, I would do 1 over, and watch what happens, everyone. 24 minus 24. And so notice I get 0 right there, and I don't even have to bother with the rest. Can I take my numbers and divide each one of those by that 0? Absolutely not. And so if you look at the top of the page, you can only find an inverse if it does have a determinant that's not 0. So we can't find the inverse of this particular matrix. And more importantly, what if I asked you to solve this system? What would you come up with? Well, the fact that our method didn't work at all, you could see, means that there are no solutions. So we were unable to solve accordingly. As soon as we figured out that there's no inverse, then you know we can't do A inverse times B, and so we can't get our variables. And if you notice in this case, if I asked you to solve by substitution or elimination, you would come up with that same variation we saw, where these are basically two parallel lines on the coordinate plane. They'll never intersect, so there are no x's and y's that make both equations true. So good. Just wanted to bring up that one piece. If the determinant is 0, there is no inverse. All right. Well, let's do some graphing calculator stuff. So I won't make you do a 3x3 inverse by hand and then use that to solve. What we'll do is just kind of set it up the same way, though. So here's what I guess I would ask. Just on your paper, can you just give me, oops, that should be an x. So when we do this, same premise, everybody. So our variables, our ordered triple in this case, would be still the inverse of A times B. Inverse of A times B. And in this case, the inverse would be a 3x3 multiplying into a 3x1, which would yet end up giving you a 3x1. You get 1, 2, 3, matching up equally with the other side. So let's give it a try. We did Kramer's rule on the graphing calculator, and to be honest, finding all of those determinants is not easy and can be cumbersome. So let's try this A inverse times B. So I'm going to go back in here and, oops, wrong one. And let's edit A. And in this case, it's going to be a 3x3. So again, let's see if you can beat me to it. Again, enter all 9 of those in. Let me make sure I have mine correct. So there's that one right there. I like to go out and go back in, but I think you could probably just hit the matrix menu again. And then let's edit B and make this the 3x1, so just the constants on the other side there. And let's get the -1 and the 1 and the -2 in. Okay, and I have that. And here's the beauty of this. You can get quicker and quicker. All I need to do to find out what the order triple is in this case is name A and take its inverse. So there's A inverse. You could put the multiplication symbol if you want, but not necessary. And then go back in and do naming B, and that should give it to us. Let's take a look. A inverse times B, and that should be our order triple. So in this case, I'm going to write it down. It looks like 2, -1, and -2. Want to be clear on that. So the x, y, and z, when all said and done, was 2, -1, and -2. Very nice, huh? Pretty efficient. There happens to be maybe just one slightly more efficient way to pull it off on the calculator. But since I haven't taught really the way to solve that system manually, then I'm not going to teach that way to solve it on the calculator. There's no real context for it. Okay, so everyone, I'm going to ask you to take a moment now and do a 4x4 inverse, and then multiply that by a 4x1 B matrix, and see if you can get this. So I'm going to just set you up right here. This will be the ordered quadruple. X, Y, Z, and W on the back end, but same premise, everyone. If you could pause the video and take a moment there. So enter in a 4x4 matrix A, then enter in a 4x1 matrix B. Once you have those, Again, just that mantra for the day, A inverse times B. And let's see what happens. So please pause the video and then come on back and I'll write the ordered quadruple on the board. All right, let's see how you did. I ended up getting 2, 1, 0, and 1 when all was said and done there. Very nice. You know, we're going to do a lot of problem solving with this stuff. I think we're going to disregard example 6 for the time being. It's a good one, but there's enough application that we're going to see over the next several days here. I don't think that that's a necessity at this point in time. So I guess really for this lesson now, we've got that fourth alternative or fourth method to solve a system of equations. By the way, as you get ready for your next assessment, please know that there is a non-calculator part to it. In terms of substitution or elimination, you're going to get your choice, but I will ask you to solve 1 or 2 of them by Cramer's rule. I will ask you to solve 1 or 2 by inverses, and I will ask you to do some matrix multiplication as well without any type of graphing calculator. I can probably give you a scientific calculator if you really need it. You shouldn't. It's not a necessity. You can probably do it without. But just please know on the next assessment, there will be a spot for no calculator. Actually, probably 2/3 of the test is no calculator. Then you'll get to pick it up and do some of this stuff here. So again, just trying to hold you accountable for some of the algebra that we're going over with, but also integrate some of the technology too to help us out. Okay, well if you have questions on that piece, let me know. Anything going on with the calculator, please let me know about that as well, and just any questions at all. Of course, thank you very much for listening. I certainly appreciate it, and you know, talk to me about any issues that you have.